Hello everyone, I'm Alka Jangir from IIT Kanpur, your TA for Basics of Materials Engineering. In today's lecture, we'll be talking about fatigue failure, and this course is offered by Professor Ratna Kumar from Department of Mechanical Engineering, IIT Madras. So firstly, we'll be going through some sample assignment questions. Then we'll be going through some lecture notes, which will be helping you in solving your assignment questions. So first question is fatigue strength for non-ferrous materials is defined at blank stress cycles. Your options are 10 to the power 3, 10 to the power 5, 10 to the power 7 or 10 to the power 9. So your answer will be 10 to the power 7. So this is how your non-ferrous materials. Okay, so this B graph is what your non-ferrous materials SN curve looks like. So in this case, there is not definite fatigue limit. So you have to define a particular number of cycles. So corresponding to that, you report your stress value. So you keep your stress below that for designing your materials. Now we can explain this by saying that fatigue failure is defined as a time delayed fracture under cyclic loading. Now materials fail under fluctuating stresses at a stress magnitude that is lower than the ultimate tensile strength of material, and sometimes it is lower than even your yield strength. So the magnitude of the stress causing fatigue failure decreases as the number of stress cycles increases. So we are seeing it is an inverse relation. So as the number of cycles is increasing, your required stress is decreasing. So this is your non-ferrous materials, and these are A is your ferrous materials and titanium alloys. Now second question is most often machine components fail by. Your options are buckling, creep, fatigue or all. Your answer will be fatigue. Now most of the failures in machine components are due to time varying loads rather than static loads. Now such failures happen at much lower stresses than yield stress, and all the designs, engineering designs, we design it based on your yield stress and the stresses that we use. So this mostly the loads are in cyclic type of behavior, so they fail well below yield stress. So static failure theories alone lead to these unsafe designs. That's why most of your machine components, they fail by fatigue. Third question is the following equation defines the SN curve. Your options are Paris equation, Baskin equation, Andrade equation or Garofalo equation. Your answer will be Baskin equation. Okay, so in case of Baskin equation, your SN curve is defined at high cycle region using this equation. So in this case, it will follow this type of power law. So in this case, your sigma is your stress amplitude, and P and C are empirical constants. So there is an empirical relationship at high cycle region. So in that part, your Baskin equation is followed. Now SN curve is determined using 8 to 12 specimens. We take multiple specimens and we vary the stress amplitude, and depending on that, number of failure cycles change. So using that, you can draw your SN curve. Your fourth question is the SN curve from a fatigue test for steel is shown. Which one of the options gives the endurance limit? Your options are SUT, S2, S3 or S4. Now here multiple stresses are given. So SUT is around your ultimate tensile strength, and this point here, it is at 0, your material will fail at ultimate tensile strength. As we keep on taking some number of cycles for fatigue loading, then your stress keeps on reducing. So now as we see here, S1, S2, S3 and S4. S4 is corresponding to N4 number of cycles. Now in case of ferrous materials, what happens, this horizontal line, this depicts your fatigue limit. Now this stress corresponding to this horizontal line is said your endurance limit. So this is S4. S4 will be your answer. The fatigue life reduces with respect to the increase in stress range, and at a limiting value of stress, the curve flattens off. The point 4 at which the SN curve flattens off is called the endurance limit. And the line between 10 to the power 3, 10 to the power 6 cycles is taken to represent high cycle fatigue. And from SN curve, we can see that the curve becomes asymptotic nearly at 10 to the power 6 cycles for steel. Now question is, which factor doesn't affect the fatigue strength of a material? Your options are temperature, microstructure, magnetic susceptibility or residual stresses. Answer will be magnetic susceptibility. And we can explain this by saying that fatigue strength of material is affected by the microstructure and mechanical properties of materials. And we know that temperature can change your microstructure of material as well. And temperature also plays an important role in defining fatigue strength and thermal fatigue. So this factor is also affecting. And stress concentration, corrosion, temperature, microstructure, residual stress and stress state are some factors affecting material fatigue strength. Now magnetic susceptibility doesn't affect the fatigue behavior of the material. Now sixth question is a numerical. So in this case, it is a cylindrical shaft is subjected to alternating stress of 100 MPa, and fatigue strength to sustain 1000 cycles is 490 MPa. If the corrected endurance strength is 70 MPa, what will be the estimated shaft life in revolutions? Revolutions means your number of cycles. And if the fatigue strength of the bar to withstand n cycles is 100 MPa, then what will be the value of n to the nearest integer? Okay, so you can consider this linear type of graph for log stress and log number of cycles. And here we know that for 1000 cycles stress is given 490, so log 490 will be equals to log 1000, and for this point will be for log 490 and log 10 will be 3, and here their log 100 will be corresponding to your log n number of cycles, and we have to find out. And for 70 it is given that it is for 70 MPa it is your endurance strength. Endurance strength we can take as your 1 million cycles, so it is taken as 6 log n. Now we have to find out the value of n. Here as it is shown, the fatigue strength of the bar is calculated using the SN diagram, where 10 to the power 3 cycles for stress is 0.9 SUT. SUT is your ultimate tensile strength times the 0.9, and for 10 to the power 6 cycles and the stress is endurance limit. Now for sigma equal to 100 MPa, we can find out the n number of cycles. For 1000 cycles, 490 MPa stress is given, which is 0.9 times the SUT, and the corrected endurance limit is given 70 MPa, and sigma E is given, which is for 10 to the power 6 cycles. So using SN curve for the equation line AB, so slope is same. So we can use this y2 minus y1 divided by x2 minus x1. So here x1 minus x2 is taken in both of these cases. So log n minus 3 divided by this log 490 minus log 100. And similarly the slope of AB will be similar. So 6 minus 3 divided by log 490 minus log 70. Now by solving this, we can get the number of cycles will be 2,81,914 cycles. Now this is another numerical. So in this, a machine element has an ultimate strength of 600 MPa. And endurance limit is 250 MPa. Now endurance limit we know 10 to the power 6 cycles will be corresponding, and ultimate strength we know it will be for 0 cycles. So for 10 to the power 3 cycles, it is given that if the element is to be designed for a finite number of cycles of 10,000 cycles, the maximum amplitude of a completely reversed operating stress is blank and MPa. Now for 10 to the power 3, it will be around 0.8 sigma u. So for this you can calculate 0.8 times this ultimate tensile strength, 600 times 0.8. Now using these coordinates again, similarly as taking a linear up to your endurance limit, we can get that for point A, it will be log 0.8 times your ultimate tensile strength, and which will be at 10 to the power 3, and then at B point it will be log S. So S we are taking the unknown stress that we have to find out corresponding to your 10,000 cycles. C will be log of endurance limit, that is given 250, and the log n for 10,000 cycles, so 1 million cycles will be your 6. So based on that previous equation, we can find out this using same y2 minus y1 upon x2 minus x1. Similarly, you can find out that stress will be 386.19. Now question 8. If the size of a standard specimen for fatigue testing machine is increased, the endurance limit for the material will. Your options are have same value as that of standard specimen, or increases, decreases, or none of these. So your answer will be decreases, because if we increase the size of the specimen, then there will be higher probability of the presence of any stress razor point. Now we can explain that when the surface finish is poor, there are scratches and geometric irregularities on the surface. These surface scratches serve as a stress razors and result in stress concentration. The endurance limit is reduced due to the introduction of stress concentration on these scratches. When the machine part is larger, the greater is the probability that a flaw exists somewhere in the component, and the chances of fatigue failure originating at these flaws are more. and the endurance limit therefore reduces with the increasing size of the component. The greater the likelihood that a part will survive, the more is the reliability factor. The reliability factor Kc depends upon the reliability that is used in the design of the component. So as a whole, we can say that the endurance limit will be reduced due to the stress concentration if the machine part is size is taken is higher. Question number 9. Now, which material shows this type of ascent curve which is shown here? So here we can see that there is a horizontal line after a particular number of cycles. So this corresponds to which material? Your options are mild steel, aluminum, or copper, or gold. Now answer will be mild steel. Now as shown here in this diagram, we can see that mild steel has higher fatigue strength, and also it shows a definite fatigue limit. So after particular number of cycles, it will not fail up to that stress. And for aluminium alloys, there won't be a definite fatigue limit. So fatigue strength is specified for an arbitrary number of cycles, such as 10 to the power 6, 10 to the power 7, or 10 to the power 8. Now non-ferrous materials, they don't show any horizontal line in the ascent curve, while ferrous materials like mild steel, they show a horizontal line because below a certain stress limit, they don't fail on even a very high number of stress cycles. One of the reasons for this behavior is strain edging because of presence of interstitial atoms such as carbon and nitrogen. Next question is, which of the following is not a theory of fatigue? Your options are Orovan theory, Griffith's theory, fatigue limit theory, or Wood's theory. Your answer will be Griffith's theory. So Griffith theory we studied in previous chapter. So it was related to your fracture mechanics rather than fatigue. So in case of fatigue, Orovan theory, fatigue life, fatigue limit theory, Wood's theory, dislocation movement theory, these are the ones that I used. Now Griffith's theory is related to fracture mechanics, while other three are related to fatigue failure. In Griffith theory, it states that a crack will propagate when the reduction in potential energy that occurs due to crack growth is greater than or equal to the increase in surface energy due to the creation of new free surfaces. And in case of Orovan theory, back and forth movement of slip causes the formation of microscopic intrusion and extrusions which act as notch for crack initiation. Other is fatigue limit theory, in which the metals which undergo strain etching have well defined fatigue limits. A specimen with less amount of nitrogen and carbon will have less tendency for strain etching, and the ascent curve will not show fatigue limit for these type of specimens. While heat treated steels, they show a definite fatigue limit. Other is Wood's theory. The metal consists of weak areas which undergo slip earlier due to favorable orientation. These regions exceed critical value and crack first. Now we'll be going through some lecture notes. So firstly, what is fatigue theory? Fatigue failure. So firstly, most of the failures in machine components are due to time varying loads rather than static loads. In case of static loads, if you are applying for example 10 MPa load, then it will be constant throughout the time. It won't be changing with different with varying time. While if it's changing, then it will be counted in fatigue failure. Such failures happen at much lower stress than yield stress. So these can be below UTS and even below yield stress, depending on what stress amplitude you are taking and other factors such as presence of cracks in specimen. Now, static failure theories alone leads to unsafe design. So, when we design materials, we consider, like for example, yield. What is yield strength of the material, and depending on that, we end up designing material without taking in consideration that there might be pre-existing cracks in material, or material can undergo your strain. Strain hardening or softening with cyclic loading and other factors. Now, failure of rail coach axles in 1800s led to the development of failure theories under dynamic loads. Now, first scientific investigation of fatigue failure was done by August Waller, which took around 12 years of careful study. 80 to 90% of all failures are due to fatigue, and annual cost of fatigue of materials to the US economy in 1982 was around $100 billions. That's about 3% of their GNP at that particular time. Now, total fatal crashes of the first commercial passenger jet aircraft, Comet is the company of aircraft, in 1954, which was due to fatigue failure of fuselage. Now, one of the fatigue failure in history is Boston molasses tank explosion. Now, this collapse was due to the rise in temperature from minus 17 degrees Celsius to 5 degrees Celsius in just 2 days. Now that led to like when the other molasses came into the pre-existing tank which had the cooler molasses, then they both because of the reaction it caused fatigue crack initiation near manhole. Now around 25 feet high wave with 56 kilometer per hour led to the killing of around 21 people and injury to around 150. Now, another example is skate derailment in Germany. Now, on 3rd June 1998 in skate, Germany, at the rail was going at 200 km per hour, and it had first high-speed train accident in the world and in the history of Germany. Around 101 people died, around 88 were injured, and it had around 287 passengers in the train. And it occurred because there was a single fatigue crack in the wheel. And previously the wheels were made using a monoblock wheel, which was at that time replaced with a dual block wheel and a layer of rubber followed by a metal layer in contact with the rail. So a dual block wheel has not been tested on a high speed train, and they simply didn't have facilities to test fatigue failure at such high speeds. An effect of dynamic loading not taken into account during designing. Now these fatigue failures, they cause huge cost involvement with fatigue failure, and also when we try to design a material in such manner that it has higher fatigue strength, that also these attempts also lead to huge cost. And fatigue failure always starts at a crack And in case of comet aeroplane failure, it started at a crack smaller than around 0.07 inch near the windows, which were almost square in shape. So these windows were very square, which led to initiation of crack easier compared to round type of shape. So dynamically loaded parts should be designed to minimize stress concentrations. And after this comet failure, the UK lost its aeroplane market completely to Boeing in USA. And a component is designed to give a certain length of service under a specified loading cycles when we try to design a material for fatigue failure. And many components of high-speed aero and turbine engines are designed for considering fatigue strength. Fatigue failure is defined as a time-delayed fracture under cyclic loading, and these materials fail under fluctuating stresses at a stress magnitude that is lower than the ultimate tensile strength of material, and sometimes the magnitude is even lower than yield strength. The magnitude of the stress causing fatigue failure decreases as the number of stress cycles increases, and the phenomena of decreased resistance of the material to fluctuating stresses is the main characteristic of fatigue failures. Now, example of parts in which fatigue failures are common are transmission parts, connecting rods, gears, ball bearings, vehicle suspension springs, etc. Now, firstly, when it was noted, this fatigue failure was by Boiler, who found that the number of cycles of time bearing stress was the culprit for these type of failures. He did this study for around 20 years in 1867. He found that there was an existence of endurance limit for steels. Example, a stress level that would be tolerable for 1,000,000 of fully reversed cycles. Now, this is how some materials will have this type of endurance limit, and some won't be showing this, and the curve will be falling further. Now this type of graph where we are drawing it stress versus number of failure cycles, this is known as either ascent curve or Euler diagram. Now there are various types of time varying stresses. So it can be fully reversed, where it will be going up to particular stress in tensile direction and in compressive direction, and the value will be same in both directions. So this is known as fully reversed. It can be repeated, where it will be in tensile only region. It can be fluctuating, where it's in tensile region, but it won't be coming to zero at all. Now these are different types of time varying stresses. Now other are in case of reversed stress cycle, in which the stress alternates from maximum tensile stress to a maximum compressive stress of equal magnitude. Sigma max and sigma minimum, their mode will be equal. Other is repeated stress cycle, where in which maximum and minimum stresses are asymmetrical relative to the zero stress level, and mean stress, range of stress, and stress amplitude are indicated here. So sigma A is your from where it's varying up to the maximum, and range will be from minus sigma max minus sigma minimum. Mean will be addition and divided by 2. Yeah, the formulas are given here. So in case of cyclic stress range, delta sigma will be your sigma max minus sigma minimum. Stress amplitude will be your sigma max minus sigma minimum divided by 2. Mean stress will be your mean, so you just have to take average of maximum and minimum. Stress ratio will be your sigma minimum divided by sigma maximum. Amplitude ratio will be your sigma A amplitude divided by sigma m, your mean stress. Now in case of fully reversed type of loading, we see that your stress ratio will be -1 and amplitude ratio will be infinite. And in case of repeated loading, will be see that R will be 0, A will be 1. Now these are the some definitions for the parameters that we saw earlier. So in case of fluctuating stress cycle characterizing parameters, first is amplitude. So the stress amplitude alternates about a mean stress, sigma m. So defined as the average of the maximum and minimum stresses in the cycles. So your mean stress will be sigma max plus sigma minimum divided by 2. And the range of stress will be sigma r, which is just the difference between maximum and minimum. And the stress amplitude is just 1/2 of this range of stress. So range divided by 2, or sigma max minus sigma minimum divided by 2. Stress ratio is just the ratio of the minimum and maximum stress amplitudes. So capital R will be your sigma minimum divided by sigma maximum. Now we have seen how your stress cycles are working. Now after certain stress cycles, your material will completely fail. So that particular number of cycles is noted on the x-axis, and on y-axis we are noting what is the amplitude of the stress. So these graphs are known as SN curves. Now fatigue is the fracture or failure of material that is subjected to repeating cyclical loading or cyclic stresses. Now there are two factors, the magnitude of loading and the number of cycles before the material fails. The behavior is different for different materials, so it is customary to show the fatigue behavior of a given material in terms of an SN curve. Here S denotes the stress amplitude and capital N denotes the number of cycles before the material fractures. In each cycle, the stress is raised to the maximum value of the extension and reversed to the same value in compression. Now there are various modes of fatigue testing. So this can be either in case of compressive and tensile forces, or it can be torsion type of loading, or it can be bending type of loading for fatigue testing. These are two different types of SN curves, so it can be having endurance limit for steels and titanium alloys having presence of some interstitial atoms, or it can be in case of various non-ferrous metals, it shows this type of behavior where it won't be showing any definite endurance limit. Fatigue or endurance limit. So the shape of the curve is of much significance to engineering results. For metals such as mild steel and titanium, the curve becomes horizontal at certain stresses. The stress is called fatigue limit or endurance limit. Below this stress, the specimen does not fail or fracture. So the material will not fail even after infinite number of stress cycles. This implies that if the material is loaded to a stress below the fatigue limit, it will not fail, no matter how many times the stress is applied. And non-ferrous metals like magnesium, aluminium and copper alloys, they do not have a true fatigue limit because the curve never becomes horizontal and the curve slopes downward with an increasing number of cycles. For such non-ferrous metals, the term fatigue strength is used to specify the fatigue properties. And fatigue strength is the stress that will cause fracture after a certain specified number of cycles. For example, 10 to the power 6 or 10 to the power 7, 10 to the power 8. The number of cycles is arbitrarily taken and it should be told at what number of cycles you have chosen your fatigue strength. Corrections to fatigue strength or endurance limit. So fatigue strength or endurance limit for materials is obtained by standard tests and there will be physical difference between the test specimen and the actual machine part. So when we are getting the value of fatigue strength or endurance limit using our test, then it will be noted as SF dash or SE dash. From the experiment, it should be corrected for the following factors. So there will be a loading factor, there will be environmental factors such as temperature. So you have to take these factors into consideration. There will be reliability factor, there will be size effect. So there will be difference in size of your test specimen and your actual machine component. There will be surface effects. These all factors should be considered. These factors will be multiplied to the experimentally obtained endurance limit. Then you will be getting the actual endurance limit of the machine component. Now, there are 3 stages of fatigue failure. First is crack initiation, second is crack propagation, third is your sudden fracture. In first stage, it involves a very short duration. Cracks initiate due to stress razors such as notches, and it is important for ductile materials due to local yielding. Second stage is crack propagation. In this second stage, it involves most of the life of the part, and tensile stress opens the crack and the compressive stress closes the crack. And the crack propagation growth rates are small. For example, it's around 10 to the power minus 8 or 10 to the power minus 4 inch per cycle. And sudden fracture due to unstable crack growth. Now this stage is instantaneous. So here the cross section of your specimen will be reduced very less, so it can't sustain that load anymore, so it will fail suddenly. So these are various stages of your fatigue failure which are shown in the specimen cross section as well. Now similarly, the process of fatigue failure is characterized by 3 distinct steps. So it is told again. So in case of crack initiation, a small crack forms at some point of high stress concentration. So these points can be because of presence of some occlusions, because of presence of some stress razors, or they can initiate because of formation of extrusion intrusions that will be studied further. And second is crack propagation, so during which this crack advances incrementally with each stress cycle. And final failure, so it occurs very rapidly once the advancing crack has reached a critical size. Now cracks associated with fatigue failure almost always initiate on the surface of a component at some point of stress concentration. Now, crack nucleation sites include surface scratches, sharp fillets, keyways, threads, dents, and the like. In addition, cyclic loading can produce microscopic surface discontinuities resulting from dislocation slip steps that may also act as stress resets and therefore as crack initiation sites. This is the image of your fracture surface. So, fracture surface of a rotating steel shaft that experienced fatigue failure. These are the beach marks and ridges which are visible in the photograph. Now, the region of a fracture surface that formed during the crack propagation step may be characterized by two types of markings termed beach marks and striations. Both of these features, they indicate the position of a crack and crack tip at the same point in time and appear as concentric ridges that expand away from the crack initiation site, frequently in a circular or semicircular manner. Now, beach marks, sometimes also called clamshell marks, are the microscopic dimensions and may be observed with the unaided eyes. Now, these are the this is the final rupture, direction of rotation, and origin of the crack. These are given in this your fracture surface. There are also some fatigue failure regimes. So, low cycle fatigue, high cycle fatigue, and these are divided by 10 to the power 3 cycles. So, if your material is falling below these cycles, then it is your low cycle fatigue, and if it is failing after these many cycles, then it is high cycle fatigue region. And there are various fatigue failure models as well. So, first is stress life approach. In this case, you'll be drawing stress on your y-axis and number of cycles on x-axis. This is the oldest way. It is often used for high cycle fatigue, where the component is expected to last for more than 10 to the power 3 cycles. It is suitable when stress and strain are mostly elastic, hence they are not suitable for low cycle fatigue where stress levels are high, leading to possible local yielding. It seeks to find fatigue strength and or an endurance limit. We can distinguish between initiation and propagation phases. Second approach is strain life approach. So you're on y-axis, you'll be plotting strain. Now, so it is suitable for low cycle fatigue. It gives good picture of crack initiation, and it is suitable when there is a significant plastic strain present. It is most complicated to implement of all the three other models. Third model is linear elastic fracture mechanics approach. In this case, it is suitable for remaining life predictions, and it is best model for crack propagation stage, and cyclic stress intensity factor is taken as the crack driver. Now, examples for this: automobile crack shaft is usually required to last for several thousand kilometers, and the number of fatigue cycles is around 2 multiplied by 10 to the power 8, which is clearly a high cycle fatigue regime. Now, aircraft bodies and ship hulls, although have many cycles of known stress, they sometimes are subjected to storms which might exceed design loads, leading to local yielding. Now, they use a strain life approach together with linear elastic failure approach. Now, factors that affect fatigue life. So, first is your mean stress. So, if we keep on increasing your mean stress, so this is what your trend will look like. So, sigma M3 is highest. So, as I'm keep on increasing mean stress, then your fatigue strength is reducing. So, as mean stress increases, your fatigue strength decreases, which is seen in this graph as well. Second is surface treatments. So, short peening, case hardening by nitriding, carburizing, etc. They enhance fatigue strength of steels. Now, in this case, you are introducing some compressive type of stresses in your surface. So, it will lead to improvement in your fatigue strength. Third is design factors. So, any notch or geometrical discontinuity can act as stress ratio and fatigue crack initiation site. So, for other is environmental factors. So, there can be thermal fatigue or corrosion fatigue, where your thermal, in this case, your temperature will aid to the fatigue, and in case of corrosion, your oxidizing environment that can lead to aiding of fatigue. Now here we can see that short paint material has shown better fatigue strength compared to normal steel. So this effect will study further. So effect of metallurgical variables on fatigue properties. So fatigue properties can be greatly improved by careful design, reduction in stress concentration. So we have to take very smooth surface of material. It should be very finely polished, and intelligent use of residual compressive stresses. So if we apply some residual stresses on the surface of material, it might lead to improve in fatigue strength of material. Controlling certain metallurgical variables. So the ratio of the fatigue limit to the yield strength to the ultimate strength is called fatigue value, and the fatigue limit of cast steel and wrought steel is about 50% of ultimate tensile strength. In case of copper, nickel and magnesium, the fatigue ratio is 0.35. Effect of mean stress. So as we keep on varying the mean stress, your number of cycles is changing. So in case of compressive mean stress, it is beneficial. So if there are presence of some compressive stresses in surface, as I told earlier, that is the reason we do short pinning of steels in case of ball bearings. And here, as we can see, when the mean stress is negative, or it's equal to 0, or it's positive, then there are different type of trend. So for compressive type of mean stress, we are seeing that it has highest fatigue strength. So generally residual compressive mean stresses are introduced in high alternating tensile stress region to improve fatigue life, and tensile loads leads to crack opening while compressive stresses close the crack tip. Next is effect of stress concentration of fatigue. So majority of machine parts contain keyways, screw threads, holes, press fits, fillets, etc. These geometrical irregularities act as stress resistors and they reduce the fatigue strength greatly. Therefore, these irregularities they must be reduced by careful design. Surface roughness also causes stress concentration, and another class of stress resistors they are called metallurgical stress resistors, which consists of inclusions, decarburization, local overheating due to grinding, porosity, etc. Now, the effect of stress resistors on fatigue is studied by preparing a specimen with a V or circular notch. When the specimen is loaded, the notch has the following effects. So, this notch acts as a triaxial state of stress which is produced, and there is a stress concentration at the root of notches, and the stress gradient is set up from the root of the notch to the center of the specimen, and owing to the stress concentration at the root a crack is developed. Now these are the reason that your surface should be finished very properly. It should be polished smooth to improve the fatigue life of your material or your machine component. Now, although several theories of fatigue have been put forward, we shall discuss briefly the following theories. First is Orban theory, second is fatigue limit theory, third is Wood's theory, fourth is dislocation moment theory. First, so in this case, according to this theory, the metal is considered to contain small weak regions along which the slip occurs easily, and the metal also contains inclusions which are impurities which act as notches and cause stress concentration around inclusion. These regions are treated as plastic regions in the elastic matrix, and they experience an increase in stress even when the repeated applied stress is constant. And this increase in stress causes plastic strain in the weak region. This plastic strain increases with increase in the applied stress on the specimen. When the plastic strain in the weak region exceeds beyond a certain value, a crack is formed, and this process is repeated again and again until a large crack is formed. Now this type of structure is there. So if we consider these grains, so in polycrystalline material, this grain is supposed to exceed the Schmidt factor earlier compared to other grains, then this grain will show plastic deformation earlier compared to these grains, and this will get strained and show strain hardening, leading to initiation of crack earlier compared to these grains. Or there can be presence of inclusions or different type of weak regions which can lead to initiation of crack. Second theory is fatigue limit theory. In this case, according to this theory, the localized strain aging effect affects the fatigue properties to a large extent, and some metals have well-defined fatigue limits while others do not show fatigue limits, and the metal which undergo strain aging have well-defined fatigue limits and a specimen. So strain aging is seen when there is presence of some interstitial atoms. So as I told earlier, there will be nitrogen or carbon atoms in case of steels or in case of titanium alloys. So those will see well-defined fatigue limits. So a specimen with less amount of nitrogen and carbon won't be showing will have less tendency for strain aging, and the SN curve will not show fatigue limit for this specimen. And in case of heat treated steels, they show a definite fatigue limit. So this endurance limit will be seen in your steels type of ferrous metals. Now third theory is Wood's theory. In this, the strain direction in fatigue is reversed again and again, and the slip produced by fatigue consists of slip bends, which are the slip movements of the order of 10 to the power minus 8 mm in length and 10 to the power minus 6 and 10 to the power minus 5 mm in height. When there is a strain in one single direction, the steps that appear are simple, and when the loading is cyclic, the slip bends they tend to group as notches on or ridges. The notch acts as a starting point for fatigue crack, and the notch with a very small root radius, it acts as a stress reserve, and cracks slowly propagates through the material, and after some time a stage will come when the remaining portion of the cross section is too small to bear the maximum load, and at this point sudden failure occurs. The final fracture is usually of cleavage type. So these type of small intrusions and extrusions will form in material, and these will act as notch in material, and it will lead us formation of crack, and then there will be crack propagation for certain number of cycles, then there will be failure of material, sudden failure of material. This theory best describes, like in various materials, how fatigue might take place. And this theory is similar to previous theory. This is dislocation movement theory. So in this, the dislocation moves during fatigue, and consequently a localized deformation occurs in slip bends, and this deformation is called extrusions. Some metal is expelled out of surface, so like this the material will come out, and the extrusions are generally accompanied by intrusions. So these inverse extrusions, these are will be seen as a notch or initiation of crack. So these extrusions and intrusions, these appear as early as 1/10 of the whole life of specimen, and have a height of 10 to the power minus 5 to 10 to the power minus 6 mm. These are responsible for the initiation of crack and further failure of material. So that's all from my side. I'll show you questions once more. Okay, so first question was, fatigue strength for non-ferrous materials is defined at blank stress cycles. So it is 10 to the power 7. Second question was, most often machine components fail by. Your answer will be fatigue. Third question was, equation defines the SN curve. It will be Baskin equation. Fourth question was, the SN curve from a fatigue test for a steel is shown. Which one of the option gives the endurance limit? It will be S4, because your curve is becoming horizontal after S4. Which factor doesn't affect the fatigue strength of material? So all factors are important except magnetic susceptibility. Sixth question is numerical. Here you just have to follow this linear equation. So slope will be equal for both. So y2 minus y1 upon x2 upon x1. For these three different points, you can equate it and find out the number of cycles. Seventh question is similar. Here also you have to find out a line, and in this there are 3 points, so you have to find out the value of stress opposed to number of cycles in previous case. In case of eighth question, you have to tell like with change in specimen size what will be effect on fatigue strength. So endurance limit will decrease with increase in size because there is probability of stress concentration razors will be higher. Ninth question is which material shows this type of ascent curve. So your answer will be mild steel because these type of steels they show this definite fatigue, finite fatigue life. So here after certain numbers your material won't fail if you keep your stress below this endurance limit. 10th question is which of the following is not a theory of fatigue. Your answer will be Griffith's theory, Orwell fatigue limit theory, and Wood's theory. These are related to fatigue. Okay, that's it from my side.